This is team number 28, and we're here to tell you about our intermittent glucose monitoring bottle for infant diabetes. Our team members include Hannah Peliquin, Christian Pyle, Stanley Bache, and Devonshea Redadia. Our team's task was to design a system that would be able to test glucose levels in premature infants in developing countries. Each year, about 15 million babies are born preterm. While preterm birth complications are the leading cause of death among children under 5 years of age, 3/4 of these deaths can be prevented with suitable, cost-effective intervention. Infant diabetes is relatively rare but can have long-term effects such as chronic hyperglycemia, dehydration, developmental delay, among others. Traditional glucometers require a blood sample, but a non-invasive method of measuring glucose are continuous glucose monitoring devices. These are usually used on a larger scale with patches on skin and use electrochemical sensors. An example of a device used in infants is a pacifier glucose sensor.
Our research objective were to design a device that is biocompatible, highly accurate, comfortable, easy to use, and low reliance on electricity. We chose saliva as a testing medium because the levels of glucose in saliva is highly correlated to that of the blood. And also, we discovered that other media presented disadvantages such as low accuracy and lag time.
We have chosen to develop a feeding bottle which collects saliva and subsequently tests for the glucose concentration. Features include 2 channels originating at the nipple, a size 0 nipple, and a bottle size of 20 ounces. Additional features include an enzymatic biosensor, an LCD and LEDs, a Bluetooth module, and removable components. The cap of our bottle will be designed to open and close either the milk channel or saliva channel as necessary. When the cap is twisted to the right, the saliva channel will be opened while the milk channel is closed. Conversely, when the cap is twisted to the left, the saliva channel will be closed while the milk channel is opened. Prior to feeding, the saliva channel will transport saliva from the infant's mouth to the enzymatic biosensor situated at the bottom of the bottle. This channel will be equipped with valves to prevent backflow. The components of a typical biosensor include the analyte, bioreceptor, transducer, signal processing unit, and a display. The analyte in this case is the glucose present in saliva, and the bioreceptor is glucose oxidase. An amperemetric sensor was selected as the transducer. The amperemetric sensor consists of 3 electrodes: the working electrode, reference electrode, and counter electrode. Glucose oxidase is deposited and immobilized on the working electrode. The reference electrode usually sets a stable reference potential, and the electric current flows between the counter and working electrodes. Glucose reacts with glucose oxidase to produce hydrogen peroxide. Hydrogen peroxide is then oxidized at a specific potential, around 600 millivolts. The loss of electrons generates a current which is proportional to the glucose concentration. The sensor will be connected to a signal processing system, which can measure the current and display the data on the LCD screen, as well as transmit the data to an app on a secondary device. The average price range for devices which utilize enzymatic biosensors is usually between 40 to 60 US dollars. Additionally, the retail price of a premature infant bottle is between 10 to 20 US dollars. With these price estimates, we can deduce that our device will be under our target price of 100 US dollars.